Hello students, in this video I am going to go over sample examples for exercise U1A00a, which is classifying types of numbers, and then right after going through this exercise I'm going to go into U1A00b, which is orders of operations. So let's take a look. So in this exercise here, what you have to do is you have to name the set or sets of the numbers that is being presented to you. And like all the exercise that we give you, which look like this in format, they're actually generated by a software called CUDA. And at the end of the exercise, okay, there is an answer key. And if you look at these answer keys, these answers look very, very cryptic. So I want to explain a little bit about what those answers mean, okay? So if you recall in the last video, okay, one of the earliest developments of our understanding of numbers in general was this idea of counting numbers, right, or natural numbers. So n represents natural. And if you recall what natural was, they are just whole numbers without the number 0. And then what exactly are whole numbers? Well, they're whole numbers, but so they're all natural numbers, okay, but with the inclusion of number 0. So these are whole numbers. So all numbers, so again, this is 1, 2, 3. This is 0, 1, 2, and 3, okay? And the next progression in our understanding after whole numbers is we have integers, which is z, which just looks really odd. So these are z, okay, integers, which is -2, -1, 0, 1, 2, and so forth. And then with our understanding maturing integers comes rational, which again looks really odd because why q, right? Well, actually rational numbers can be thought of as a quotient. Remember in the previous video that you viewed, rational numbers are numbers that can be expressed as a fraction. So rational numbers can be thought of as quotients, and these are all numbers that have terminating decimal points, okay, or can be expressed as a fraction. And then the next progression is we have rational, we also have irrational, which is given by the letter I. Whoops. So in this, these are the sets of numbers that you are going to be working with here. We have five different sets of numbers. Let me see if I missed one here unintentionally. Natural, whole, integers, rational, irrational. Oh, I forgot one really important one. So all of these numbers, okay, are under the classification of real. Okay, all of these numbers are under the classification of real. And as a matter of fact, all of these numbers here, okay, as you can see, they are all actually real numbers. But anyway, let's take a look, okay, at some of the examples. All right, so I'm going to go through some of the odd questions here. So square root of 783 over 3. Let's see if this can be reduced by any means here. So square root of 783 over 3 can turn into, let's see, 3 goes into 7 twice with 1 left over, and then it's going to be 6, 1. So this is square root of 261. Can 261 be reduced any further afterwards? It looks like it cannot, because can I divide 261 by 2? It certainly cannot. Can I divide it by 3? No. Looks like that won't work either. So this is actually going to be, we can't go any further, and this is going to be irrational, because if I punch this into a calculator, square root of 261 turns into a non-repeating decimal. So let's take a look at that really quickly. If I take square root of 261, whoops, let's clear everything. Let's clear everything. So I have square root of 261. I do end up with a non-repeating set of numbers here. So this turns into, and again, if you're wondering whether or not, like, very, very far down the line to the right, whether or not the calculator is actually displaying this fully or not. How can we conclude whether or not this is actually irrational? I would encourage you to break this up into its prime forms, right? If we can break this up even further, okay, you can see that none of those factors turn into perfect squares. So anyway, this is going to be irrational, so this deserves the letter I. This is also part of a real number. Okay, 17 over 4. This is actually going to be rational, and it's a real number. 20 over 7 is again a rational number, and it's a real number. 216 over 2, let's see here. This turns into square root of, let's see here, 108. And square root of 108 is actually not a perfect square. Because it's not a perfect square, I immediately know that this is not going to be it's not going to be rational. So this is going to be actually irrational. And it's a real number. -5 is an integer. So this is an integer. And it's a real number. And actually, not only that, these integers, okay, can also be classified as rational. Because can I express -5 as a fraction? I most certainly can. It's -5 over 1. Okay? And square root of 73. So this is going to be irrational and real. Square root of 45, again, it's irrational and real. There's a lot of irrationals here. And then this is going to be rational and real. 60 over 32 can be reduced to, well, positive 60 over 32. The end result here, it's going to be end up being a rational number and real, but this will turn into 30 over 16 or 15 over 8, right? 18 over 15, this is, again, rational and real. Square root of 0, this is actually a whole number. It's a whole number, it's a real number. Can I express this as a rational? I certainly can, because 0 is also 0 over 1, right? Is it a natural number? It's not a natural number. Is it a counting number? It's not a counting number. This is also an integer as well. This is a part of the integer, right? It's also an integer.